talking about ammonia, the key to hydrogen storage and the transition to clean carbon-free energy. We are happy to welcome Dr. Agustin Valera Medina. He is a professor at Cardiff School of Engineering. He has participated in many industrial projects, including projects with Pemex, Rolls-Royce, Siemens, Airbus, and Flow Gas. He has over 225 papers, and 101 of these papers are specifically concerning ammonia power. Professor Valero Medina led Cardiff's contribution to the innovative UK decoupled green energy project that lasted from 2015 to 2018, led by Siemens and in partnership with STFC and the University of Oxford. And this project had the goal to demonstrate the use of green ammonia produced from wind energy. So I believe that he's going to talk to us about all of these. He's going to tell us a little bit more. And we are very interested in learning more about this kind of transition to clean, carbon-free types of energy. So welcome to Cicata today, and I'm going to hand over to you this conference, and to everybody. If you have questions, you can ask them at the end of the presentation. Okay, thank you very much.
Muchas gracias por la introducción. De antemano, les comento, soy mexicano, como bien mencionaba la doctora, y he estado trabajando en el Reino Unido. Entonces, la presentación será en inglés, pues para darle no solamente un estilo como lo presentamos en los seminarios a nivel internacional, sino también para poder apoyarlos con el aprendizaje y entendimiento del idioma. Entonces, cualquier pregunta, ya sea en inglés o en español, en el momento que terminemos la presentación, es más que bienvenida. Ok, entonces con eso empiezo la presentación, espero les agrade, y de nuevo cualquier comentario o pregunta, por favor háganmela saber.
Ok, doctor.
Ok, ¿pueden ver mi presentación? Perfecto. Ok,
sí,
sí, perfecto. Muy bien, muchas gracias. Okay, perfect. So I'll start the presentation, and I'll be talking about green ammonia as an energy vector. As mentioned previously in my biography, I've been working a lot on this subject, and we have found that it's a very interesting area that, as mentioned to Gabby, who politely and nicely contacted me a few weeks ago to support this venture, this idea of having these seminars. I talked to her and told her that it was an interesting concept at the time that we started working on it, and eventually just progressing to something that has just reached all the corners of the planet. So as part of the content that I'll introduce and mention across my presentation, I'll be mentioning about the introduction, the challenges that we face, developments that we have been doing on the subject, and then collaborations with some conclusions regarding the use of this interesting chemical for its power and energy associates. So this is in a nutshell some of my biography. For those that want to read, go ahead. But then the idea is that I can then use this time to then mention something about the subject on its own and how it reached our university at some point, just at the end of 2013, before Christmas. And along those lines, we had some people from Siemens coming over and saying, we want to burn ammonia. We didn't understand what they were trying to do. We've been working on combustion in my university, Cardiff, for around 40 years now. And we have some pedigree on combustion systems, but we never thought about burning ammonia. And when I started digging out some information about the use of this chemical, I found out that at some point in the last century, some companies and some institutions were trying actually to burn ammonia and then progress from fossil fuels to net zero vectors like this one. But interestingly, what happened was that at some point, one of the main problems was that the emissions, the lack of efficiencies, and some other factors they led to the stop and finish of these programs. That eventually we'll just recap, and then we'll resume at the beginning of 2000, and then by the beginning of 2010-12, Japanese start working on this concept, and now we have institutions all across the world working on it. We know about industries, large clusters actually trying to use it in China, Japan, South Korea. The marine industry is moving in that direction, so it's forecast now that 1/3 of all marine vessels worldwide in the next 15 years will be operating with ammonia, and in the same way with turbines and other large power systems, medium-sized and small-scale units will be using the vector in different locations. So again, like very promising, and it was just a combination between luck and the hard work that we have put on this area that have allowed us to then reach this level of expertise. So with that, everything comes down to why we want to use ammonia, and it goes to then using these renewable sources that we have been talking about for the last 20, 30 years. Those include marine, wind, and solar. And as probably all of you know, we have lots of issues regarding intermittency. Just in the UK, we had around 5 years ago this main issue that because we were running at that particular day at around 40% wind power, then the wind stopped. There were some issues regarding weather in the north of Scotland, and then from there, we just stopped producing that energy. So around 1 million people lost power during that those couple of days. Similarly, something happened in Australia where they were just fitting and charging some batteries in the south region of the country, and then eventually what happened was that they suffered a problem with the batteries and also the feeding of that energy, and eventually an entire city lost its power for just a few hours. Again, just like raising the importance of having some way of actually storing some of that energy. This is a graph that was produced a few years back by Siemens, and what they did was to evaluate different vectors, different methods to actually store energy. And probably you've seen many, as like those related to batteries. We have flywheel storage, supercapacitors that, again, at the time are just moving into now early commercial stages, pump hydro, and some thermomechanical storage as well, like compressed air in caves and some other locations. But the one that is very promising, we have been using for centuries, even millennia, and it has been in our agenda, has always been chemicals. And with that, we have natural gas, or mainly methane, 90%, hydrogen, that is been in the scope of research over the last 30 years, and then ammonia, that we've been looking into for a nice period of around 10, 12 years, with a lot of scope and a lot of industrial push to then get it going. So this is an interesting map and also some techno-economic analysis performed by the Hydrogen Council. And what they're concerned about is actually looking into how hydrogen could be moved around different locations where we will have all this massive production of the renewable energy, and then probably tapping into it to produce hydrogen. And what's what we do? Then we can then move it around to those locations where we're going to be needing it and using it the most. So they are putting some cases like Chile to the US, Saudi Arabia to the European Union, and Australia to Japan. And along those lines, you can see on the left-hand side that we got all these photovoltaic wind resources spread all around the globe, compared to what would be the natural gas resources that are very localized and again now are in depletion mode. So with that, the Hydrogen Council said, well, if we are going to then have a place like, for example, in Chile, that we're going to produce lots of wind and solar power, then hydrogen being produced and then delivering it to the US, if we compare ammonia, liquefied hydrogen, and liquid organic hydrogen carriers, then we need to then analyze what will be the cost from the clean production to the final ports when we're going to be distributing this chemical. And you can see from the right-hand side that the cost at port is fairly the same between the cases of the one, ammonia, the second, liquefied hydrogen, and the liquid organic hydrogen carriers. But there's one catch, because the thing is that with the ammonia, we have almost a 1/3 component of that cost. So what that means is that we can then reduce the cracking of the ammonia, then we will then have the best and most economic solution to then deliver all that energy, making then ammonia a perfect case for long distance distribution, for long storage, and also, as you'll see, in the heavy duty workloads. So with that, ammonia can be recovered from renewable energies. We can as well use stranded resources like placing islands or very far away from the off-grid locations, enable the use of waste streams because we can then recover things from farms or processes that have lots of nitrogen ammonia in it, allow storage of vast amount of energy, and it can be as well much cheaper than the use of hydrogen as we know it right now, be used to produce energy from these isolated locations, be employed not only as a fertilizer, that is the main use of ammonia, but also as a fuel. And one of the interesting things is that hydrogen in content inside of the ammonia molecule is actually more than the one that you will have in the hydrogen molecule. And the reason is that you got 3 atoms of hydrogen in the ammonia molecule, therefore around 20 to 35% more hydrogen in ammonia than in hydrogen itself. And there's a massive infrastructure with a market that is almost worth 200 billion euros per year because it's the second most commercialized chemical worldwide. And that makes ammonia a very interesting, a fantastic case to then distribute that hydrogen and then provide for some of that energy. One of the questions that I always get is, okay, so we are going to then produce all this ammonia, but then what is going to happen with the fertilizers that we're now producing? Are they going to then get compromised in the production of this ammonia energy? Well, different companies are now looking into different technologies and the transition through all these different generations of systems. So the first one, the one that appears in purple in this graph, is one that we have been using for now 100 years. That is called the Haber-Bosch process. So we employ some natural gas, we mix it with steam, and then out of that we get lots of hydrogen and then put it together with nitrogen from the atmosphere, react them, and finally produce the ammonia. Main challenge and problem with that is that we are producing lots of CO2 that eventually is just dumped into the atmosphere, contributing between 3 to 4% of the total human production CO2 that the civilization is producing nowadays. So it's a massive contributor to climate change. Therefore, companies are looking into what is generation 2 that appears in this graph in blue and is using renewable energy to then produce via electrolysis the hydrogen that will then mix with the nitrogen from atmosphere, then put it into these reactors. And then one that has the potential of actually changing the world and probably the next Nobel Prize would be Generation 3. Generation 3 is a combination of surface catalysis and materials in cells, fuel cells that are going to use the renewable energy, going to then mix water and nitrogen straight from the air, so without having to then separate it, and then finally producing the ammonia. If that happens at some point in the near long future, what that means that anyone that has renewable energy, as we've seen in the map, in the previous map, is almost every corner of the planet, water and air available, will be able to store that energy in form of ammonia. So therefore, will change drastically all the concept on how we produce, store, and distribute energy worldwide. Another interesting way to actually produce that ammonia is called pink ammonia production. And is now looking into the use of thorium reactors via nuclear energy. And this is an interesting concept because these nuclear reactors are very small, the size of a classroom. And with that, they're pretending to produce around 100 megawatts per container, and then pile them up, we'll get gigawatts of power that will produce lots of heat that can be employed for ammonia. Ammonia that will go and be distributed via shipping and containers, and that way decentralize the production of energy in these isolated locations. So a combination between nuclear and ammonia is now in the cards of every company that is actually thinking about producing ammonia for the near future. With that, we got all these different aspects. We got renewable energies that can be used to then feed directly into the grid. Then we have some others that will be produced to then produce hydrogen that can as well be produced for the case of transport, heating and cooling, process industries. And then finally, those that will require long distance distribution, shipping, or then be redirected to isolated locations, making ammonia a perfect case to then deal with those combinations. One of the main issues is that we still don't understand fully what is happening with the reactions and combustion of these ammonia molecules, because the nitrogen molecule, it seems very tricky and difficult to understand. Public perception analysis, how the public is going to then act to then start using ammonia, because ammonia is toxic in nature. Regulations, we don't have any regulations to start using as a fuel. The only one that we got at the moment is one from the IMO, that is a technical specification and some ideas to then start using in shipping industry, the economics involved with that, and then finally the environmental aspects that will come, thus dumping all the water and nitrogen from the process that we're producing, as long as with the combustion or use of ammonia. Here, there's a table that shows how the case of ammonia is very interesting in terms of carbon-based fuels and those that are zero carbon. And out of the zero carbon, those that, again, we tend to use, that are lithium batteries, or the case of hydrogen, can compare to ammonia. Ammonia is superior in energy density per liter that we'll get from the fuel itself. That is close to the methanol. And in terms of what is the cost of distribution and storage, you can see shipping, rail, and lorries then compare to then what is hydrogen and ammonia. ¿Sí? ¿Hay alguna pregunta? No? Okay. So, yeah, with that in mind, we got all these different vectors that we've been talking about: hydrogen, ammonia, methane, and methanol. And this is another study, very interesting, produced by the University of Louvain in Belgium. And what they did was to analyze what would be the final efficiency in systems operating on these different fuels. As you can see, in the case of hydrogen, we get at the final end from the tapping of renewable energy to the final end of using it in a system that's got some thermal electrical efficiency around 17%. So from the total amount of energy, just 17% is what is going to be finally used for this type of process. And the main reason is that we're missing a lot of, we're losing a lot of energy in just the storage of the hydrogen itself. But in the cases of ammonia, methane, and methanol, the final efficiencies are pretty similar, between 24 to 26%, making then ammonia the best case because it's the one that won't have any carbon emissions tagged to it. So along those lines, some other studies by the University of Minnesota conducted in all these different cities that you see in the graph were looking into what would be the levelized cost of electricity of using the ammonia, hydrogen, or a combination of both. And it was found that when you can combine both, therefore have small storage facilities with a small renewable size sources recovery, you would get the best combination of both chemicals, and with that supplement each other to then provide for the best levelized cost of electricity. Therefore, ammonia is an excellent complement to this hydrogen transition, and therefore will be part of what is going to come in the following years. And that was something that the International Energy Agency realized in 2018. So they put it, ammonia, as part of the energy applications that the chemical could provide for power industry and shipping. And then after that, lots of different institutions and governmental bodies across Europe, Asia, and also here, for example, in UK, start realizing the potential of using ammonia, with many funds and large programs that are now running at different scales. So with that, ammonia can be used in all these systems that you see here, from fuel cells in PEM, alkaline or solid oxide, internal combustion engines, combined cycles using gas turbines and some other bottoming systems, and then furnaces and boilers at all these different efficiencies, running from the 3540 to around 9095 that you can then recover from the use of the chemical. All have challenges, all require some mitigation, some advanced research and innovation in terms of engineering and technology, but all are feasible and possible at their capacities, with lots of research going on now in this arena. And in terms of what is going on in different locations, particularly to Mexico, a recent report produced by Ricardo and EDF, the Environmental Defense Fund, look into what will be the potential of Mexico of actually using ammonia as one of these suppliers worldwide that can provide for the fuel itself. And what they found was that Mexico has an amazing potential because of its ports and its renewable energy sources to then produce all that amount of chemical and then supply places like the US with ammonia from renewable sources. Similarly, and not that long ago, just 3-4 weeks ago, we heard in the news that the Istmo de Tehuantepec was receiving a new company called Helax, and what they are going to do is produce ammonia for fueling and shipping applications. So now companies are establishing themselves in Mexico to tap into renewable sources produced in the region, and then with that produce ammonia and hydrogen that will be used for shipping and power applications. So this is coming to Mexico and is coming across all the world, especially Asia, Japan, China, South Korea, that are leading this subject very strong to then decarbonize their systems. So we got lots of challenges. We have identified 4 that are particular to these technologies, and they are related to then first the synthesis of free carbon ammonia. Then the second one is production of energy at power utility scale. We have public acceptance that is a major issue that requires safe regulations and community engagement. And then finally, the economics that need to be right before we can then start tapping and producing all these ammonia for fueling applications. So along those lines, some of the things and developments that we have done, we focus, as you've seen in my biography, on the area of combustion, is looking into what would happen if we change some ammonia by hydrogen or hydrogen by ammonia in flame profiles. And this is important because once that we start doing the switch between hydrogen to ammonia, then we experience different patterns of the final flame that could be good in some cases, could be very bad in some others. So just as an example, you have this figure where you have different contents of hydrogen from 20%, 0.2, to then 100% hydrogen, and different pressures that we were testing inside of a chamber. And as you can see, once that we start increasing the pressure and the amount of hydrogen, you have all these wrinkles that appear at the flame front. Those wrinkles are instabilities that are really bad for combustion systems. So what that means is that if we increase the pressure using pure hydrogen, as you would expect in now the new gas turbine systems that have been promised from lots of companies, you will start getting these instabilities at the flame front, then producing very nasty effects that can potentially lead to the loss of the flame and explosions inside of the gas turbine components. With that, we also have studied along the years some of these patterns of the changes of what would be the radicals and the different formation of species across the flame front. You can see on the top left-hand side that you got a blue, nice methane flame, as the one that we got in our stoves, and then one that is 80% of ammonia, and that going to the orange. So changes in those radicals will change as well what is the profile of the flame in colors, in stretching, in its efficiency to be born, etc. And with that, different aspects that have to do with this same combination of hydrogen ammonia inside of pipelines. So this, again, thinking about how we can then stabilize it using, for example, internal combustion engines, gas turbines, or boilers. For those that are interested in numerical modeling, there's a lot of work going on as well, because we are trying to understand some of these instabilities, these patterns that happen at different concentrations of ammonia. So some of the works that are experimentally being done, that one in red, has been correlated to the one that is in blue, that is all numerically modeled. So by direct numerical simulations, what we have been doing with some of our partners is looking into what would be the effect of changing that hydrogen content at different air conditions. And as you can see, as we are increasing the amount of hydrogen, therefore less ammonia, 25% ammonia means that 75 hydrogen has been used for that test, is that we got all those wrinkles appearing at the flame front. Again, nasty if we put them into an internal combustion engine. Another study and fundamentals that we have been doing is focused on the radiation that we can produce via ammonia. And this is something that is of importance, especially for processes like cement production, like steel making, or even glass melting. And with that, we have identified that ammonia has less radiation, produces less radiation than natural gas. However, if you start using some of oxygen, additional oxygen, into these flame fronts, then you can increase the radiation, reduce CO2 emissions, therefore have a much better profile and pattern to the one that you will get with natural gas. So therefore being promising for the production of cement, steel, and glass in these industries. Some of the works that have been going on in Japan, and this is as well a very at the forefront of what is going on, state of the art in terms of ammonia, is the injection of the chemical via liquid injection without using any gasification. And this particular set of experiments is for a company called IHI. IHI is one of the biggest manufacturers in Japan, and they were trying to do is produce gas turbines that will operate solely with ammonia. And then with that, using these injection streams to then produce these patterns and then avoid the vaporization of the chemical. Another area that we're exploring that is fascinating is the use of plasmas. Plasmas that can be imposed on the use of these combustion systems. And one of the things that is happening is that once that we create the plasma, around 3 to 5% the energy coming from the flame, then we improve the radical formation and therefore the stabilization of the flame. Another thing that we are finding is that we can reduce emissions as well coming from the flame by using plasmas. And different use of plasmas, different types, can then be used in the future for even aerospace applications. So this is some of the work that we have been doing. We have looked into the reduction of emissions. We have been developing our own burners, and then all these profiles are already in the public domain, showing how the use of our plasmas is actually producing a much better profile of these type of flames. Some other works that we have been doing, again, utility scale, that we appear to see when it comes to using this chemical. Some of the things that are very interesting is that by changing the geometries, by changing the method of injection, we have different NOx patterns, we have different emissions, we got some different stabilities, and therefore it's a very complex subject because, again, once you change a little bit of these geometries, the changes in what is the ignition delay, burning durations, emissions, just drastically changes in that context. So that's the reason, because there's a lot of research going on trying to then normalize some of these tests. So eventually someone comes up with a final solution or a solution that is as approachable as possible to engineering applications that can be just used for general purposes worldwide. Some of the ideas regarding the use of spark ignition, supporting reaction control systems, as well in line with these thoughts to then produce something that is stable and that can reduce as well the emissions produced by such systems. When it comes to boilers and furnaces, we do have a lot of work going on. So these are just two systems that you can see, three actually. One that is being used for refineries and oil systems that uses ammonia, and once that it recovers from these locations, then produce some extra power for steam production. Steel making is, as you can see from the two flames, the one that is blue, natural gas, the one that is yellow, the one that is that's based on ammonia. In Japan, going for the annealing process and production of steel making. And then the one that you see on the bottom is the first ceramic tile produced worldwide that was produced using purely ammonia. And all that line that you see there is around 20 meters long. Now China is using a 200 meters long ammonia line to produce tiles using green ammonia. And that they're just trying to expand it to 200 companies in the region of Guangzhou and Shenzhen. So with that, we have been working on the idea and principle of replacing LPG here in the UK. So propane is being used in lots of rural locations. And after doing some techno-economic analysis, we have found that the best way to replace the LPG would be to use ammonia. And I get always the question, why ammonia if hydrogen is actually being used for ammonia production? Isn't it supposed to then be more expensive to use ammonia instead? But the answer to that is that if we were bringing hydrogen containers, we would need many more hydrogen containers than those that we require for ammonia to then provide for the same energy. Therefore, the use of ammonia is superior in these type of locations to the use of hydrogen itself, plus all the requirements that have to do with health and safety. Along those lines, the use of ammonia in coal power plants is going ahead. There are now news about using it in Japan, using it in China, that is now proliferating quickly and extremely fast because they have a very big program of around $500 million just dedicated to research on ammonia technologies for decarbonization of coal power plants. It's going on in South Korea, in Malaysia, in Thailand, and also now in India and also Indonesia. So with that, the proliferation of these technologies called replacement based on ammonia is going ahead. And as I mentioned, some of the interesting aspects is that once you start changing some of the bits of the technology, as you can see here on the left-hand side, just the angle will be enough to then increase or decrease the amount of emissions that you would get from these systems, which is, again, fascinating, a big challenge in terms of engineering, but a fascinating area to then do research on. As part of that, some of the CFD modeling that we have been doing have allowed us to then develop our own burner, and then with that, try systems that go up to 1 megawatt power into boiler applications. So the one that you see at the very bottom, that is a furnace that can go up to 3.5 megawatts. We are running it at half megawatt. And then the boiler that you see on the left-hand side, that one will operate at 1 megawatt power using ammonia solely. So you see the ammonia drum that we got is half a ton, and that one provides energy for at least a week and a half for that same unit, which is, again, pretty good. And as part of that, we have been doing works on the use of novel materials. Catalysis is going to be a major one because we believe that you require some hydrogen that can be obtained actually from the ammonia itself. So we partially crack or decompose the ammonia, then what will happen is that we'll produce some of that hydrogen that will improve our ammonia combustion. In the same way, we are testing different materials to do this cracking. We are testing what would happen inside of the combustion chambers in terms of instabilities. We also evaluate what is the radiation. And now another area that we are using is artificial intelligence and machine learning. With artificial intelligence and machine learning, what we are doing is providing some new controllers that are going to then feed into these units to then determine what is the right amount of ammonia hydrogen that we require. And then based on the visualization of the flames, then we can determine what is the oxygen fuel content and therefore control it.
Problemas de la combustión de amoníaco. Es que de repente se me va el avión. Es la producción de óxidos de nitrógeno. Ya regresó.
Así es, así es. ¿Me escuchan bien?
Bueno, sí, ya nos doctor, muchas gracias. Estamos aquí discutiendo un poco sobre lo que eventualmente serán los residuos, pero lo escuchamos desde donde se quedó y ya después podemos tener la discusión. Muchísimas gracias.
Perfecto, perfecto. No, and that's actually one of the main issues. And the interesting thing is that as you start increasing the amount of ammonia inside of these flames, you reduce the NOx that are produced at the flame front. So, for example, in this case, you can see that we had loss of oxygen, ultra lean, then we call it lean, that we have some oxygen. And then when we have the perfect combination of oxygen and ammonia, then the NO, NO2, N2O drastically decay. Now you have some increase in the traces of what is the onboard ammonia, but again, in parts per million is negligible compared to what the hundreds of NO that you have reduced. Because ammonia is a natural denoxing agent that is being used in power stations and also other systems. So finding the right combination and right amount of ammonia nitrogen oxides is what is needed for these systems. So along those lines, we have different systems related to large power boilers and furnace applications. We're now looking into the use of small systems as well, pellet-based, and with materials and catalytic converters to provide energy at low power. Thinking about domestic appliances, around 1 to 2 kilowatts power that could potentially feed using ammonia, using catalytic materials that decompose the ammonia, produce hydrogen, and then at the same time, by the recombination of NOxes, can reduce the NOxes at the front of these materials. So that's another area that we have been looking at. In terms of gas turbines, we have been working on this area for a long time. And again, going back to that point mentioned about the nitrogen oxides, we have this graph that is at the left-hand side, and it shows how as we increase the amount of ammonia, that is that pie that you see there, is where we have the reduction of nitrogen oxides with an increase of onboard ammonia. Because there's a combination, a sweet spot between both of them, where we actually are decomposing any nitrogen oxides by the onboard ammonia. That's the sweet spot that we need for this type of applications. Another thing that is very interesting is that we start then producing loss of hydrogen at the flame front. And that's the reason, because in some of these applications, we require a secondary zone that is going to burn only that production of hydrogen. And because hydrogen has been produced in the range of 2 to 5%, it's above this flammability limit. Therefore, we can do the combustion properly. Some of the things that we have done as well have to do with the normalization of species, and that to then find out what is the perfect status of the flame that we are using. And this goes back to the artificial intelligence systems that I was talking about. So one of the things that you see here, depending on the amount of ammonia, you will have different graphs for different radicals. But then once that you start normalizing these values, then you have some of these trends that are linear, and that can give you a really nice scope of where you are in terms of the amount of oxygen fuel that you got in the system. So if these can be combined with that artificial intelligence and also machine learning from the images being recorded from the flames, you can then have a clever, intelligent controller that can provide for the right amount of ammonia that is required in the systems. Other things that we have been looking at is also material science, materials impacts on how we have these changes of the material surface and embrittlement that can happen via hydrogen getting inside of the material. Some of the things that have to do as well with nitration at the surface of steels and nickel-based alloys. And for example, in the case that you see here on the left-hand side is Inconel that we're exposing to ammonia hydrogen blends. And as you can see, the A is the one that has been exposed to ammonia hydrogen. It's been entirely nitrated plus with the embrittlement that it suffered in the graph below. And the one that is B has been exposed just to natural gas and nothing major across the system, with very little embrittlement being produced, even again less than the one that could be measured in some of the cases. On the other side, we got all this steel analysis done by the University of Tokyo. And what you can see is that the one that is at the beginning, just untreated materials, they have that different grain and very stable. And then as they've been just exposed to an ammonia oxygenated flame, they have just changed entirely in terms of the structure of the material. Some of the programs that we got are larger scale. So we're trying to decarbonize a large power station in Portugal. And with that, we are looking into the use and replacement of the hydrogen and ammonia inside of a power unit. Interesting thing is that we don't stop the gas turbine. We keep operating it. And then when we are off the grid or a very low power requirements, then we use that extra power to produce the ammonia. And once that we are back to peak hour demand, we can then input that ammonia or then crack it and produce hydrogen nitrogen to then feed the additional power that is required from the gas turbine. So that way we keep the operation ongoing, we reduce the sizing of the gas turbine, and therefore reduce costs at the end of the day. So with that, we have done some tests and experiments related to this area at different pressures. And as you can see, once that we start increasing the pressure, we just get to the reduction as well of nitrogen oxides. This is an interesting aspect of the technology, because what happens is that once we have the increase of reactivity, the compression of the flame, and also the increase of reactivity, then nitrogen oxides tend to decrease. Now, there's a point that they start flattening out and they just remain continuous and constant at the same value, but there's a point where they can be reduced drastically from 2 to 3 times in terms of gas turbine operation. And that's what now operators and manufacturers are looking at for the pressures and systems operating with potentially ammonia hydrogen blends. With that, some works that we have done numerically with Baker Hughes are showing that same trend, that as we start increasing that amount of ammonia inside of our blends and also changing the pressures, we have a drastic reduction in nitrogen oxides coming from these systems. So you see here how we had around 1,000 parts per million in this particular system when we're operating at 1.1 equivalence ratio, that is slightly passing the points of a perfect combination air fuel. And then once that we increased it further, it was in the range of around just 3 to 10 parts per million. With that, some of the works that we have been doing are in propulsion systems. Ammonia is being used over the years for aerospace applications in the US, where they try them in oxy-fuel-based type of systems, in the same way that Russia, China, and some other economies like the UK or Europe have been using it in satellites. However, one of the things that people are now looking at, and this goes back to Boeing and NASA, are in collaboration with Florida and Georgia Tech, they are now evaluating the use of ammonia for air flights and aerospace systems. And here we did a comparison where we were comparing jet fuel with liquefied biomass, liquefied ammonia, and liquefied hydrogen. You can see that from the very beginning, compared to what is your jet fuel, around 39% of the overall haul would be possible using ammonia, compared with just 29% with hydrogen. Therefore, making ammonia again a very interesting feasible solution to then use. However, there are some challenges, again, not thermodynamically, because you can see here power ratios, shaft speeds, etc. All these patterns are already, again, similar to those that we obtain from jet fuel, but some that have to do with especially toxicity. So here on this table that we got on the right-hand side, we got all the different aspects compared by this group in Germany, where they were doing analysis between the cases of jet fuel with some fossil blends, methanol, methane, hydrogen ammonia, and hydrogen ammonia. And the one that is very bad for the case of ammonia hydrogen, that would be the one that is the worst case problematic, is the one that is toxicity related, and things that have to do with health and safety. However, along those lines, now companies are looking into how to use and bring ammonia on board, start cracking it or producing some partial cracking, and therefore providing for the power that is required in gas turbines, engines, and even fuel cells for aerospace applications. And finally, some of these works that we have done as well in the past have to do with health and safety and environment, because ammonia, as I've said, is toxic, can produce very nasty mist, and is a chemical that can then dehydrate the skin and some other organs. As you can see here in this case, exposure of the skins to anhydrous ammonia has just literally killed the skin in this individual. Similarly, could produce explosions because of a chemical that is flammable, and therefore we need to then be careful about how to use it. However, a lot of companies and different institutions have looked into these details, and they have compared some other fuels to what ammonia could do. The first one, table 10.6, that comes from a report that looked into what were the fatalities across the US in a period of around 50 years. And you can see it's less than 40 over the years, which means that, again, with the right conditions, the right regulations, there's no fear of using the ammonia. Now, this goes back as a fertilizer, is not being as used as a fuel, but the idea is that any regulation moving forward will then be dealt by people that are properly trained to then use the chemical. The Environmental Defense Fund, what they did was analyze oil spills versus ammonia spills in tankers and ship containers. And as you can see, what will be the receptors and the impact on each of them, the cases of oil and ammonia are pretty similar, with the difference being especially for the case of oil in invertebrates and also birds, and in the case of ammonia on fish, because again of that change in the pH that could happen once that ammonia is spilled in water. And then finally, some cases looking into the comparison of propane, gasoline, and ammonia by a Danish institute. What they did was evaluate ammonia as a fuel for cars, and then finding out that if we were using ammonia, it would be better than using propane because of the flammability of propane in these type of locations. So by the end, the use of ammonia close to the road and then further away would be first superior to gasoline, and then would be superior to propane, and from the close to the furthest away locations, respectively. Some other works that we have done, looking into how we can replace these into the emissions profiles, and then finding that if we do the right after treatment of engines, these engines using ammonia could be even less damaging than those working on gasoline or diesel. And finally, some work that we have done on public perception. We did it with a PhD student that was from Mexico, was brilliant, because we managed to then compare the UK and Mexican economies in different locations with different groups, and then finding out what were the major problems on public perception using this chemical. And it was very interesting. If you can see at the top, the right-hand side, that we got two major bars, 2 and 3, that are different between countries. The first one being poisonous, the second one being the smelly nature of the chemical. And as you can see, the UK and British people would be more concerned about the smell compared to the Mexicans that are more concerned about the toxicity of the chemical. And this being said, is related to then the regulations that in the UK are more strict, are followed, and in the case of Mexico are then loose and sometimes then tend to be bended. So with that, aerospace, power generation, gas turbines, shipping are now in line to then start using ammonia in the next 5 to 10 years. We got lots of collaborations going on across different countries, including Mexico. And with that, we have produced different books, journals, papers, and modules that are related to the use of the chemical. So if anyone's interested in learning more, knowing more about this, please give us a shout, because we believe that finally, again, ammonia can be used to decarbonize cooling, heating, power, and propulsion. It's going to be a system that requires high efficiencies, low NOx emissions, and also the production of species that can be combined to then improve the process itself. There are a lot of niche applications for the use of ammonia compared to some other chemicals that are net zero. And then finally, this is a fascinating subject that, again, is just started, as I've said, around 10 years ago. And it's still a lot of legs, a lot of distance to go before we can actually have it in the way that we should to then commercialize in the long term. So this is my team. This is all my PhD students, researchers, and technicians working in our programs. If anyone's got any question, I'd be happy to answer it.
Well, thank you very much, Doctor. I wanted to ask you, you're telling us that ammonia can be cracked, and this is the process that you are using. You're changing it into hydrogen and nitrogen. And I wanted to ask you, I think I missed it. I don't know if you are going to be using a coal fuel to use it, or it's just going to be ammonia.
No, it's going to be only ammonia. So the way that we are now operating, and most of the people working around this area, there are now a lot of companies, especially in Germany, UK, China, and Japan, that are trying to then work around this topic. And initially, we operate with something that is warming up our cracking systems. So material-based, they tend to be ruthenium, nickel, and now people are talking about cobalt and also molybdenum to then use in these combinations that they're putting forward. And then with that, once that we heat it up using, for example, natural gas, propane, or electrical systems, then the ammonia comes in, starts producing hydrogen, and then once we got the hydrogen out, they can then use it either for fuel cells, directly in combustion, or as we are doing it, partially combustion systems.
Okay, thank you very much. Does anybody else have a question?
Hi, Doctor. How can be ensured that the production of ammonia green is sustainable and it not can be negative externalities?
That's a very good question, actually. The Ammonia Energy Association is a 250 industrial cluster that was created around 20 years ago, and they have been strengthening the reach. And one of the things that they are trying to do is certify the production of either blue, green, pink, or even yellow ammonia. Now, the way that this company is trying to go is that they can then produce this green as sustainable as possible. Now you have the challenge of requiring still water that you need to get into electrolysis systems, and also the sizing of your systems that are operating for the electrolysis. So therefore requiring a lot of rare earths or expensive, difficult to obtain materials, which doesn't make any of these components sustainable at all. So that's one of the things that now these companies are trying to evaluate and then come up with some ideas to then reduce the amount of water, fresh water that can be used in the process, thinking that actually salty water can be replaced. So if that happens in, again, next 5-10 years, will be a very big step forward because it will increase the sustainability of these systems. Anyone with salty water close to the beach, we got the sun, you got all that water resource, then potentially produce the energy, the ammonia. And the other one, again, on these components, then try to then maximize them, improve the materials that have been used, move into something that is less complex. As I said, we are now talking about materials that are ruthenium-based, selenium, and some other elements that are more difficult to obtain than nickel or iron. So if that happens as well, that will increase the sustainability of these processes. At the point of in time right now is that it's still not sustainable, still it's very expensive, and still is in the core of research for material components, techno-economics, and again, reliability. So we still have a very long way to go before we can say that we got sustainable green ammonia.
Thank you.
Questions? Okay, I think this is a very important question that Gabby was telling us because the environmental concern is very high right now, especially in developing countries like Mexico, where we are still fighting to make the environment more sustainable for everybody, especially to the people who work in mining sectors or people who don't have the same resources as other people do. So I believe that this is a main concern. And as I was telling you, this is what we were discussing before when we lost connection. So I would like for you to tell us, do you have a plan after this is well established and you have the companies already interested in this technology? Do you have a plan as to how to manage the waste that will eventually be produced?
Yes, no, it's a very good question, and actually one that these companies are already working on. So now there are many projects, around 100, that have been promised by the end of this decade that will be operating to produce green ammonia. Now, the whole idea is that as part of this development that has been ongoing, is working with institutions that can then provide for new materials and new methods to then provide more sustainable solutions that can tap into, again, salty water and then materials that are easy to obtain. And for example, the US, they have put forward a budget of around $500 million to then get into that area. In the case of Japan, it goes around as well, 350, 500 million dollars to then develop this type of technologies. China is moving as well into the billions of dollars to then get it done. Because, first of all, in our case, for example, we want to use it as a fuel. And it's, again, a nice way to then decarbonize our industries. But mainly, what people are interested in these companies that are producing the ammonia is that they want it as a fertilizer. That's where the market is. And once that the shipping industry, the power generators start asking for the ammonia, it will come probably at the beginning of next decade. But right now is how we can reduce that 4% CO2 that we're producing and emitting to the atmosphere. And the only way to then do it is by using these green technologies. But they need to then make it sustainable, especially, again, concerning what would be the total cost coming from, again, using cases like fresh water in locations that are already depleted in fresh water. So sustainability is a major topic of all these companies working on the production of ammonia. Again, looking into how they can improve the materials. And in the case of the US, there's a program called ARENA, and what they are doing is looking into the development of these new materials. In the case of Japan, they are working as well with new methods of actually producing the ammonia via plasmas and again, catalytic components. And in cases of Australia, they are now looking into the generation 3 aspect. They are saying close to 40-46% efficiencies compared to around 57-60 that the Haber-Bosch process is producing. So they're getting closer to what is required. And in other cases, like in Europe, everything has been around materials, catalysis, and so on. So there's a lot of push on the area of catalysis. That's where the main money is going to. In the cases of us, using it for energy generation, and there's a lot of companies now looking into it because they say, well, if we start with something, it will need to then be potentially what is called blue ammonia. And that blue is that we sequestrate the CO2, but with the aim that we finally get to then the green agenda. And we get to the green agenda not only in a sustainable way, but also cost effective, because still producing green ammonia, because of the water that we require, the electrolysis, energy, and size of components, is still twice the cost of having conventional ammonia. So yes, it's the money is going especially into how we can reduce the process, how we can improve production, and how we can then tap into things that are already relegated, like salty water, to produce the chemical.
Okay, we have time for one last question.
Thank you, Doctor. And I was thinking, just like in all the presentation, we see that these ammonia engines are like for big applications. Even in the last slide, we see that it was like you believe it will remain in each applications. But what's the big challenge for these kind of engines, like better processing of rare earths, or like making new mixtures with other sources of energy? So in order we can make these engines more like the next car engine or truck engine, that we can make it more available. Why is it so difficult to transition nowadays to this kind of technology in smaller, more commercial applications?
Yes, no, one of the main issues when it comes to the smaller systems is the fugitive ammonia and nitrogen oxides that you produce. Because the issue is when you're working with a combustion system like a gas turbine or a boiler, then you have more control on where your air flows and the injection of species. So for example, in our case, to then reduce the NOxes, what we do is produce some onboard ammonia once we have passed the flame, and then with the nitrogen oxides that have been formed, we recombine them, and that way we reduce both of them. But in the case of an internal combustion engine, because you have less control, because you have the change in volume and pressure, and also the timing, then that's what is causing the tricky component, the tricky aspect of them putting into more conventional technologies that can be deployed in a smaller size. That being one. The second one is the public perception. So as I said, the main issue, for example, with trucks that were used during World War II was that the smell of ammonia, these fugitive ammonia emissions, was just too much. So cities across Belgium, especially Brussels, they were just smelly and nasty during those periods of time. I mean, the trucks were working properly, but the issue was that they were not cleaning up the system enough to then actually avoid those emissions. And that caused a lot of problems, again, with nuisance coming from the technology. Another one is the training of specialized equipment and staff that is required to then deliver the ammonia. So you will have, in the case of gasoline, that sometimes you have leakage or sometimes you have spills that, again, we know how to deal with some absorbent material. But if it was ammonia, then because it has this lethal toxic aspect, it could be potentially a killer for anyone that was exposed at the right concentrations of the chemical. So it needs to then be done by properly trained staff and with systems that are properly manufactured. That doesn't exist yet. But again, that same thing that doesn't exist is needed right now in the industry to actually make that change. And this will be happening in the shipping industry, because the shipping industry will require not only new regulations and new methods, but also systems like automated robotics and also bunkering that is properly done and handled by, again, people that are not trained per se on the use of ammonia. So this opens lots of opportunities for engineering applications and technology development, which I think is, again, fantastic. But that's a fantastic question, because that is the main reason, because we don't have ammonia engines operating. It has been thought that in the long term, trucks and systems that can have very long hauls and distances to travel, those are the ones that will be operating with ammonia, because of its properties of hydrogen storage. But there's potential as well in cities and other locations if we manage to then get rid of those concerns.
Okay, well, thank you very much, Dr. Valera. This is all the time we have today, and we really appreciate it, and you explaining all of this to us. I just want to make a quick reminder to our students that Dr. Valera will be in our conference in October. So we will have the opportunity to know more about his work. And there is only one last question I want to ask you, Dr. Valera. When you eventually win the Nobel Prize, will you come here to Cicata and share your experience with us?
I would love to be there. Actually, one of the things that we are trying to do is to work more in collaboration. It was a very pleasant surprise to actually get Gabby's emails asking me to then join this fabulous venture, an event that you're organizing. I wish that next year I will be there in face person to then be working with you. But as I've said, we are very keen on collaborating. I had very nice memories and good experience working with IPN. And I wish that any of you students, staff, or researchers working on any subject related to fueling is interested in ammonia, and we can make contact and then work together. From my side, I'm more than open and very happy to collaborate.
Thank you. Thank you very much. And also thank you very much to Gabby, because she created this collaboration. We're very proud of you. Thank you. And today, on behalf of the National Polytechnic Institute and Cicata Querétaro, I want to present you with this acknowledgement of your participation with this conference, Ammonia for Net Zero Carbon Energy, and is signed by our headmaster director, Dr. Juan Bautista Hurtado Ramos. Thank you very much, and we hope to see you soon here. Thank you very much. Have a good night.
Thank you very much, everyone, and es un placer. Cuídense y nos vemos pronto.
Gracias, nos vemos pronto. Hasta luego.
Gracias, bye.